Good morning, everybody. So we are now in the open channel flow. In the open channel flow, non-uniform flow we are dealing with. When we are dealing with the non-uniform flow, we have two things here. To be frank, three. The first one is specific energy that we completed in three lectures, and then we have taken up gradually varied flow, which we have discussed for 8 lectures. Then the last item, rapidly varied flow. In the rapidly varied flow, the most important concept is hydraulic jump. So the first lecture we explained about the hydraulic jump and the general equation for the hydraulic jump. In the second lecture, we confine ourselves to a rectangular channel, and in the rectangular channel, what is the equation for hydraulic jump, and then actually what is the relation between the initial depth and sequent depth. So the depth relation that we have derived in terms of the discharge per unit width, and also in terms of the Froude number of the incoming flow. Kindly remember that the Froude number of the post jump depth is not important at all. What is important for us is the incoming flow. Froude number is very important for us while analyzing the hydraulic jump. So hydraulic jump always is associated with the loss of energy. So this class is meant for to discuss on the what is the loss of energy when a hydraulic jump forms in a rectangular channel, because we are confining ourselves to only rectangular channel. What is that loss of energy? What is the equation for it? How to derive that equation we will study. Once that is completed, then what are the applications of hydraulic jump, right? And after that, we close this topic and at this stage. And in the next lecture, we will discuss only on problems related to rapidly varied flow. So this complete rapidly varied flow is 4 lectures, gradually varied flow is 8 lectures, and specific energy 3 lectures. So with that, the entire non-uniform flow is covered. So this is how you should remember, note the things. So with this, without much delay, we go into the derivation part of loss of energy. Remember that always a hydraulic rapidly varied flow results in formation of hydraulic jump. Hydraulic jump formation is always associated with basically loss of energy. And what is that loss of energy? Because we create the hydraulic jump to dissipate the energy. We create the conditions such that a hydraulic jump forms. So when a hydraulic jump forms, what are the basically the and what is the amount of energy that is lost? If hydraulic jump don't form, what will happen to that energy? How much destruction happens because of that energy? To prevent that destruction, we create the conditions for hydraulic jump under certain circumstances. Thereby, we help to dissipate the energy of the flowing water, and then we take the water downstream. This is what the process is. Now let us go into straight away the derivation part of how to derive the equation for loss of energy, right? So this lecture is to derive the expression for loss of energy due to hydraulic jump. The expression is very simple to derive, absolutely nothing, no difficulty at all. Kindly follow. Kindly remember that when a hydraulic jump forms, when a hydraulic jump forms, whenever loss of energy takes place, loss of energy takes place. Why loss of energy takes place? Due to formation of eddies and turbulence. What is eddies? Eddies are nothing but actually this is cross currents. Cross current means cross flow. So that means when flow happens, there is a cross flow to it. That is what we call it as eddies. Apart from that, turbulence, lot of mixing happens. So this is the two. Because of these two, loss of energy takes place. And how to get the loss of energy? Actually, the loss of energy is equal to the loss of energy is equal to the difference of, please remember, the difference of the specific energies between two sections. Between two sections. The sections are such that one is before the hydraulic jump, the other one is after the hydraulic jump. That you should remember. So that means how it happens actually. If I take this is the thing channel. So when a hydraulic jump forms, this is how the cross current and turbulence will be there. So this is the depth of flow before formation and this is the depth of flow after formation of the hydraulic jump. So because of this, if I call this section as 1 1 and this section as 2 2, if you calculate the energy at section, specific energy at section 1, specific energy at section 2 and difference of this, we call it as basically that is the loss of energy. So this is addition turbulence. Now I take it. So what is loss of energy? Let us straight away go into the equation. Loss of energy is nothing but the specific energy at section basically 1 minus specific energy at section 2 if I write this as. So what is specific energy at section 1? We know the specific energy equation. It is nothing but y1 plus v1 squared by 2g minus y2 plus v2 squared by 2g. Y plus v squared by 2g, y1 plus v1 squared by 2g is the specific energy at section 1 and y2 plus v2 squared by 2g is equal to the specific energy at section 2. The difference of the specific energy is nothing but the loss of energy. Then I will take actually delta E is equal to, if I bring actually suppose that this side, so V1 squared by 2g minus V2 squared by 2g, right, and this I will take it on that side y2 basically minus y1, right, if I take it on that other side. So this is the first thing. Then afterwards what is Q is equal to, you know that A1 V1 is equal to A2 V2. So A is equal to BY1 into V1. It is equal to BY2 into V2. So if I write small q is equal to capital Q by B is equal to, it is Y1 V1, right, is equal to y2 v2. Therefore I can write v1 is equal to q by y1 and v2 is equal to q by y2. So if I write, so delta E is equal to, what we are doing is v1 squared by 2g minus v2 squared by 2g minus y2 minus y1. Then actually what we mentioned, this v1 can be replaced by, it is q by y1 and V2 is equal to Q2, Q by, sorry, not Q2, Q by Y2. So if I write delta E is equal to Q square by 2GY1 square minus Q square by 2GY2 square. This is 1 minus Y2 minus Y1. This is what we can write. Then after writing it, if I take Q squared by 2G outside, it is 1 by Y1 square minus 1 by Y2 square minus Y2 minus Y1. Right? Then if I expand it, Q square by 2G into Y2 square minus Y1 square by Y1 square Y2 square minus Y2 Y1. Am I right? If you take LCM as Y1 square Y2 square, this will be. But what is the hydraulic jump equation? The hydraulic jump equation for rectangular channels, we are considering only rectangular channels, is Q square by 2Q square by G is equal to Y1 Y2 into Y1 plus Y2, which I have already derived. So here it is Q square by 2G, here it is 2Q square. So I want to multiply this equation with the 2 basically on the thing. If I multiply 2 with numerator and denominator, it is 4Q square by 2G is equal to Y1 Y2 into Y1 plus Y2. Then so now instead of Q square by 2G, this if I substitute in this equation, then if I take it, you see it, what is happening? What is Q square by 2G here? It is nothing but Q square by 2G is equal to, no, 1 second. It is equal to Y1 Y2 into Y1 plus Y2 divided by 4, right? Then so now replacing that, if I replace it, then what I will get actually, so instead of Q square by 2G, if I write Y1 Y2 into Y1 plus Y2 by 4 into, see the equation, into Y2 squared minus Y1 squared by basically Y1 square Y2 square minus Y2 minus Y1. This is all equal to delta E, right? Only thing is that Q squared by 2G I replaced. So everything is now in terms of Y1, Y2. So now what is happening? Let us see one after the other. So 1 by 4, right? Into Y1, Y2 into basically, right? Y1, Y2, Y1 plus Y2 into Y2 square minus Y1 square by Y1 square Y2 square minus Y2 minus Y1. So 1 Y1, 1 we will cancel. So 1 by 4 into Y1 plus Y2 into Y2 square minus Y1 square by Y1 Y2 minus of Y2 minus Y1. Still I try to simplify it. If I try to simplify it, basically, now what I will do, total I will do it. It is Y1 plus Y2 into Y2 squared minus Y1 square, right? Minus 4Y1 Y2 into Y2 minus Y1 whole divided by 4Y1 Y2. So now this also I brought under the same thing. Now if I do it, this is if I take it Y1 plus Y2, so Y2 minus Y1, okay, this is fine. So now what I can write, Y1 plus Y2, this is okay, and this what I will write, Y2 plus Y1 into Y2 minus Y1, right? Minus 4Y1 Y2 into Y2 minus Y1 by 4Y1. Fine. So Y2 minus, So if I take common y2 minus y1 by 4y1 y2, you bring outside. Then go inside. What is happening? Inside what will be there? Here it is y1 plus y2 into y1 plus y2 minus 4y1 y2. This is what it's. So y2 minus y1 by 4y1 y2 into, so y1 plus y2 whole square is what? Y1 square plus y2 square plus 2y1 y2 minus 4y1. So what? It is y2 minus y1 divided by 4y1 y2 into y1 square plus y2 square minus 2y1 y2. So it is what? Y2 minus y1 divided by 4y1 into y2 minus y1 whole square. So what finally? It is y2 minus y1 whole cube by 4y. So this is there. So what is loss of energy? Y2 minus y1 whole cube by 4y. So this is the equation. Right? Next, this is the derivation. What is the length of jump? Some characteristics of jump. Length of jump, very, very important equation. Length of jump is nothing but 5 to 7 times height of jump. Then what is height of jump? It is y2 minus y1 is called as the height of the jump. So these are two things that you should know. And people will ask actually, what are the various types of jumps? Just to remember, have an idea, types of jumps. There are 5 types of jumps which we call it as, it is angular jump, right? Then second one is oscillating jump. Third one is the steady jump. Sorry, before oscillating, 1 second, 1 second. This is the second one is basically a weak jump. Third one is oscillating jump. Fourth one is steady jump. Strong jump. These are only for quiz questions, you should remember. This means anywhere types of jumps are classified based on Froude number 1. That is Froude number of incoming flow. Froude number of incoming flow. So if this Froude number is between 1 to 1.7, we call it as basically angular jump. And if this is 1.7 to 2.5, we call it as weak jump. And if this Froude number is, for example, 2.5 to 4.5, this is oscillating jump. And this Froude number is 4.5 to 9, we call steady jump. And if the Froude number is greater than 9, we call it as strong jump. Here actually the dissipation of energy is poor. Dissipation of energy, if you take it, is poor in the first one. And second is also very small basically, right? And then basically even if you take it here also in oscillating also very small. Only in steady jump you can see from 45 to 75% energy is dissipated, and here up to 85% energy is dissipated. So if you create a strong jump, 85% of the energy of the incoming flow can be dissipated. And if you create a steady jump, we can dissipate up to an energy of 75 maximum. So 75 or 70, whatever it is, doesn't matter. It is 70%. So the remaining three jumps, very small energy, 20%, 25%, like that, the energy is dissipated. Once this is over, one important small question is, what are the applications of hydraulic jump? What are the applications of hydraulic jump? This is the next question. Not question, but we need to know actually. So naturally it has many practical applications. Many practical applications. What are they? I will list two, three so that you can write. So if I take it normally, it is useful. Hydraulic jump is useful to dissipate energy, to dissipate energy of flowing water, right? Energy of flowing water over spillways and other hydraulic structures and other hydraulic structures. This is the first thing. So now basically by creating the by dissipating the energy, the the what you call it as the what we can say is we can start the erosion on downstream side. The erosion on downstream side can be controlled. This is what is the main purpose of doing it. For example, if you imagine, if you don't create the hydraulic jump, and as it is, whatever the water that flows over the spillway, you allow it in directly into the channel on the downstream side, the entire downstream channel gets washed away because of the tremendous energy. So that's why we create an hydraulic jump at the foot of the spillway. Suppose if you take it, this is the spillway. If you imagine this is the spillway, here what we do is the spillway, we have a stilling basin, right? This is the stilling basin. This is what we call it as stilling basin. Sometimes we create a bucket here, so the whatever water that falls, it falls in this actually, and here actually like this the dissipation, and it flows downstream side. So this depth is y1 and y2. So if suppose this dissipation is not taking place here, then automatically the entire energy, this entire thing, directly if it falls onto the channel bed, the entire channel bed gets eroded. So this is actually a stilling basin where water is there in this and directly this flow, which is having tremendous energy, this kinetic energy, when once it meets, when a supercritical flow meets a subcritical flow, hydraulic jump forms, and by the formation of hydraulic jump, turbulence and eddies are formed. Because of that, the energy is dissipated. Because of dissipation of energy, only this portion only you have to really make a concrete apron. After that, the whole thing can be an earthen channel because the whole energy is dissipated in this portion itself. 85% of the energy of the flow is dissipated, is destroyed here itself, and then only the remaining 15%, anyhow that is only flow depth energy, that is enough, that will be flowing into the channel. So this is the first application of hydraulic jump. And if I take second application of hydraulic jump is in to raise the water level in irrigation channels. Because by creating the hydraulic jump, you see the water level suddenly increases to raise the water levels in the channels. We create there, the purpose is not just only energy dissipation, to raise the water level also in the channels. We will use this hydraulic jump can be used there. We will allow what you call it as a weak jump or an oscillating jump, so that first water level rises, which we can use it. And third one is actually it is it increases the discharge. It increases the discharge. It increases the discharge through a sluice by holding back tailwater. Then fourth one, it is basically it is used to thoroughly mix chemicals. In chemical industries, we create jump to create that what you call it as turbulence. Thereby thorough mixing of chemicals happens. The last one is to counterbalance the uplift pressure in hydraulic structures. Suppose if you see it generally, if suppose any hydraulic structure, if you see it, so whatever we are doing it, this is how it forms. Dimension, right? When the water falls here and there, this is how it happens. So this is the entire floor of the hydraulic structure. On this floor, water always seeps here, and this pressure applied on this structure by water flowing beneath the structure is called uplift. Now, because of the hydraulic jump, there is a large quantity of water on the other side. So, this weight of water will be acting downwards. So, uplift is acting upwards. This water is acting downwards. So, because of that, it is counterbalancing that. So, that's why the effect of uplift pressure is reduced. So, these are the applications. So, now finally, I will close it all the points just once again reminding it the closure of this topic, the whole rapidly varied flow. 2 minutes I will take. What are the things that we have studied? The first thing that you should know is initial depth. That means before the formation of hydraulic jump Y1. The other depth is called as sequent depth. It is Y2. These two depths together we call it as conjugate depths. What do you mean by conjugate depths? Specific force same, specific force constant. Then what is specific force? Specific force F is equal to Q square by AG plus AZ bar. Right? This is, and this itself is called as the jump equation. That is Q square by GA1 plus A1 Z1 bar is equal to Q square by GA2 plus A2 Z2 bar. This is the basically the jump equation. Then last point, fifth point in that. That is over. Now for rectangular channels we take. This is only up to here general. For rectangular channels if I take, right, what is the first equation? 2q square by g is equal to y1 y2 into y1 plus y2. This is the first equation. Then what I have derived sixth equation, y2 is equal to minus y1 by 2 plus or minus square root of y1 square by 4 basically plus 2q square by gy1. This is the thing. And if you want the other way also, I can write y1 is equal to what? Minus y2 by 2 plus or minus square root of y2 square by 4 plus 2q square by gy2. Then next seventh. In terms of round number of I can write minus y1 by 2. Basically it is not minus, just into, because minus thing I removed. Square root of 1 plus 8f1 square, 8y1 square minus 1. This is next equation. The same equation I wrote in terms of round number of the incoming flow. Then what is height of jump? Height of jump is what? Height of jump is equal to y2 minus y1. Then what is length of jump? 5 to 7 times y2 minus y1. Then last, what is the energy loss or head loss? Is equal to y2 minus y1 whole cube by 4y1 y2. Then last, in the problems people will ask what is the power loss. Power loss is equal to gamma into q into this head loss. This is nothing but this. So these are the equations. If you know this thoroughly 2-3 times, if you work on that, then I will take you to the problems. So my next task is to do as many problems as possible in this topic. So in this topic, if I take it, if anybody gives anything in rapidly varied flow means, first thing you should remember the hydraulic jump equation for rectangular channels and general equation, and then energy loss, and then problems. This is the thing. So here I will stop my lecture and I will take the next. In the next lecture, the problems I will take it in the next lecture.
Like, share, and subscribe. Hit the bell icon for more updates.